So let's get started. And if you have any questions, you can interject at any time. I think I forgot to say that last time. Like, you can always just raise your hand or interrupt me, politely, but that's fine. And I do like to try to take questions as you have them. Now, so last time at the end of class, I stated the epsilon-delta definition for the limit, and I'm going to start with that. So, definition, if for each epsilon greater than 0, there exists delta greater than 0, such that 0 less than value of x minus a less than delta implies the value of f of x minus L is less than epsilon, then we say the limit as x goes to a of f of x is equal to L. Now, there's some fine print that I wrote last class that I haven't written this time, right? Last class, at the start of the definition, I wrote this sentence about A being in a deleted open ball of the neighborhood. Remember that? So I don't want to write that all the time in here because it's going to really drain our energy. But it should be understood, though, that this point A, in order for this to make sense, it has to be, in order for the double-sided limit to make sense, it has to be a point where you can go to the left and to the right of the point, and you have the domain of the function defined there. Now, one of the things I should have emphasized more at the end of last class is that the point A itself, it doesn't have to be in the domain of the function. So we can take the limit of a function at a point that's just outside its domain, all right? That's fine. Now, if you're like me, when you first saw this definition, you're just kind of like, what? It's just hieroglyphics, right? Let's try to unpack what this means geometrically, all right? So what is this statement? Absolute value of f of x minus L less than epsilon. What's that mean? See, if we state this in terms of distance, what this says is that the distance from y equals to f of x to y equals to L is at most epsilon, right? That's what it means, right? If you take the absolute value of the difference between two numbers, it calculates the distance between those two numbers. You guys remember that from previous work? Yeah. And how about this other one? So how about this statement? 0 less than absolute value of x minus a less than delta. What does that say? What does that tell you about the distance? That's also a distance statement, right? That says the distance from x to a is at most delta. And what else? What does this side of it tell you? What cannot we have? We cannot have 0 equal to the absolute value of x minus a, right? What does that mean? That means that x is not equal to a as we consider such x, all right? So, and x not equal to a. So, if we want to make a picture of what's going on here, if this is a function, well, this is not a function, this is just a axis so far, right? But if the function looks like that, right? And maybe the point doesn't have to be in the domain, right? So could be, say, here. So I'll draw a little hole in the graph, right? But maybe this is This is what we call L, the limiting value. All right? And the limit point here is what I've denoted by A, right? And what's this definition say? It says for each epsilon greater than 0, all right, there exists a delta such that when x is within delta units of A, f of x is within epsilon units of L. So this has to happen for each epsilon greater than 0, right? That's the starting point. So what does that look like geometrically when you say the distance from y equals f of x to y equals L is the most epsilon? Well, if you look at that means that you're within this like horizontal band, like this. So here's L plus epsilon, L minus epsilon, right? So we're focusing our attention on this horizontal band. And, you know, I really need some colored chalk. Just give me a second here. I'll go hunting. Hey, do you know what colored chalk is? No. Don't have any candy? Yeah. I know what it's in the. I'm in the middle. Okay. I go. I know where. I know it's over there. I just wonder if they're any nearby. But it's okay. Sorry. Thanks, Frank. So. So. All right. So then, this condition. Where can you guys tell me on this graph? I'll have to use like shading, but if you look at it, right in here, this part of the graph, right? See that part? This part right here, here we have, if you pick an x that's between like here and here, any x in there, the output gives you an f of x, which is within epsilon units of L, right? Like if you're beyond those points, like, well, it's still okay over here. Let me just sort of exacerbate the issue and say, woo, it wasn't like that. There. Fine, whatever. Now, so just here, our output's within there, right? But, so then what this says is, if the limit exists, once you pick that epsilon band, you can choose a delta, you can zoom in close enough to A, right? Such that you fit the graph within that little zoom window. So here, I should make my delta like at most this. See that? Oh, I'm bad. Look, if I did that, that wouldn't be good because, no, yeah, that's good, that's good. I'm an idiot. Let me see here. I have trouble committing to choices. A minus delta, A plus delta. That's x, right? So if you look at just this little box right here, this little zoom window, you can see that the graph of the function, it's in there, right? And so that's what this means for the limit to exist. Basically what this means is that if the limiting value is L, and you look at y values close to L, right, you can force the graph to be within this little view window if you squeeze the horizontal, the x down far enough. And that's what it means for the limit to exist. All right? It's okay that the function doesn't have, like that's point outside the domain, that's okay. The limit's still defined. All right? So this definition means that graphically. What it's saying intuitively is that if you zoom in on the graph of the function doesn't like jump away from the limiting value really, really close to the point. Right? So here, let me show you an example of a function with a limit that wouldn't exist. So maybe the function looks something like this. All right? The function could look like that. And if we had a graph that had a jump in it like that, right? If you tried to make this right here the limiting value, right? You pick a particular epsilon band, for example, this one, right? it doesn't matter how much you shrink your delta band, right? No matter how small you make it, what happens? You're picking up these down here, right? And these have f of x, L minus f of x greater than epsilon. Like they're further, they're outside the band. And it doesn't matter how much you shrink the delta, you can't fix it. There's no small enough delta to fix it. So this would be an example of a function where the limit does not exist at a. All right? Does that make sense? I hope. Now, there are two other kinds of limits we can define, right? Because for this one, maybe let me give some numbers here. Let's suppose that this is like, 4, and let's suppose this down here is what? What do you think that is? What, -2 maybe? So what we'd like to say in this case is the following. For this graph, we have that the limit. So here, what we will say for this is the limit as x approaches a. And do you want me to give a number? A is equal to what? Maybe it looks like it's about the same as 4, right? So maybe it's a little bit more. Let's make it 5, just for the sake of contrast. So what this says is that the limit as x approaches 5. Now, see, that's not that. This right here does not exist. So we write does not exist for doesn't, because again, we can't satisfy the definition for the double-sided limit. However, what we can say is that the limit as x approaches 5, and then we need a notation, like from this side, right? From the left. So since the values are more negative than the limit point, we write a little minus up here like that. That's our notation for this. And we say limit as x approaches 5 from the left of f of x is 4. All right? And the limit as x approaches 5 from the right, so this little plus means we're like over here, right? So if you just consider values to the right, the limit of f of x is equal to what? Minus 2. Right? So this is called the left limit. And this is called the right limit. And if I just talk about limit without qualification, I'm always talking about the double-sided limit, which we defined last class, and I wrote again here over there. So like double-sided limits only exist what's a theorem? Can you kind of see it? What's going to be the relation between the double-sided limit and the left and the right limit? There's a theorem we can state, right? The limit as x approaches a of f of x equals to L is only going to be true if the limit as x approaches a from the left of f of x is equal to L, and the limit as x approaches a from the right of f of x is equal to L. So for the double-sided limit to exist, we need that both the right and the left limits, they both match up and they're equal. When they both match up and are equal, then the double-sided limit exists. All right? But you can see we'd like to have a left and a right limit to talk about things too, right? Because sometimes like your function will have a domain which has an endpoint or something, and it's nice to have a left and a right limit to take care of those end cases as well, okay? And it also gives us a way to define things. Like when your graph has this kind of feature, when the left and the right limits both exist, right, but they're different, then this is what's called a finite jump discontinuity, right? This is a finite jump discontinuity. So you guys, in pre-calculus, you talked about other kinds of discontinuities, right? Remember? No? How about this? So what I'm going to do here, for at least the first few minutes, is I'm just going to talk about limits graphically, all right? There is, if you look at my notes, there's also a careful epsilon-delta definition for the left and the right limits, right? But I'm not going to write those in class. You can look at them in the notes and like, they're there, okay? But I'm not going to eat up too much of our class time with all those, with all of the definitions. Like my notes have all of the definitions, right? So if you're ever curious about like what is the precise definition of this term, it's in there, all right? But what I'm trying to do in class is kind of keep it a little bit more high level. So anyway, so there are other kinds of limits besides just this double-sided limits or this left and this right limit, right? Like, what's the other kind of limit we talk about sometimes? We talk about like horizontal asymptotes. We talk about vertical asymptotes, right? How do those work? Let me just draw a picture for you. If we had a function that looked like this, right? And say this is pi over 2, and this is minus pi over 2, right? Can you tell me, what would we say about the limit as x goes to what of f of x equals to pi over 2? And what about the limit, you fill in the blank for me, as x goes to what of f of x is equal to minus pi over 2? So what's our notation like? If you're getting really, 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 really large for your inputs, then this kind of limit is, we're talking about x going to infinity, right? So we write x goes to infinity is pi over 2 for if a graph of the function looks like this. In other words, you can make the graph as close as you possibly want to pi over 2 if you take the inputs to be large enough. This is what the limit going to infinity is talking about. For values which are sufficiently large, you can get as close as you like to the limiting value, right? And likewise, for values sufficiently large in magnitude and negative, you have the limit as x goes to minus infinity, right? Can anybody tell me what the formula for f of x is? What is this function? What is this mystery function? Man, this chalk is miserable. I'm sorry, guys. I got to find better chalk. What if I had this graph? Would you recognize this one? This is y equals what? Can you recognize this graph anywhere? Anybody? Tangent, right. This is tangent x. What's this one? Well, but if you just take this, right, and you exchange y and x, right, you flip it over, right? No. If you reflect that graph across the line y equals x, you get this one. The vertical asymptotes of that are the horizontal asymptotes of this. This is the inverse tangent. Now, you said cotangent, but remember, did you say cotangent? You said cotangent. Somebody said cotangent. Cotangent was in the water. Cotangent's 1 over tangent, right? And 1 over tangent is not inverse tangent, right? This is inverse tangent, which is, that means what? what does inverse tangent mean? That means like tangent of inverse tangent of x equals to x, right? That's what inverse tangent means. It's the inverse with respect to function composition. In contrast, cotangent, what's cotangent? This is 1 over tangent x, right? So that's a different animal altogether. So that's the multiplicative inverse of tangent. It's very different than the function inverse of tangent. I think the graph of cotangent looks a lot like tangent. It's like...
It's the lines the other way.
Yeah. So anyway, what do we call these horizontal, right? If we set this equal to y, if you set this equal to y, these are horizontal asymptotes, right? Horizontal asymptotes. There's like horizontal asymptote of pi over 2 as you're going to plus infinity. There's a horizontal asymptote of minus pi over 2 as you're going to minus infinity. Again, I have careful definitions for what I mean by those terms in the notes, but I want to talk about it with you intuitively instead of writing those definitions down. So this kind of limit, does this have anything directly to do with the limit I've been defining at the start of class? I would argue no, right? This is a different concept of limit. But we use the same notation for both, right? Because they both have this idea of eventuality, of approaching something, right? These ones were approaching larger and larger values. In contrast, this one, we're zooming more and more into the limit point at a finite number, right? But we use both of these limiting concepts to describe some geometric aspect of graphs, right? Now this one, can you tell me, in contrast here, what would the limit? And now this is the kind of limit we have been talking about. I'm going to talk about the, let's see here, let's go to pi over 2 from this side. What would I write? X goes to pi over 2. Do I need a plus or a minus if I'm approaching it like so? Well, look at this. At pi over 2, I'm to the left of pi over 2, so we put a minus. That's our convention. That is a thing, right? It is going to the right, like the limiting process is going to the right, but you're on the left of the limit point. So I mean, there is a potential. That's why I'm talking about it. There's a potential for confusion. So that has something. And how about the limit as x approaches? Now we'll do the plus. Where would that be? What would that be? And let me erase that that errant cotangent x. It's just sitting there for no particular reason, except for conversation. So how about these? These are both left. These are left and right limits, right? So it's the same kind of thing I was just talking about. But do these limits exist? I mean, I don't think so, right? So for this one, as we're approaching from this way, it's getting larger and larger and larger without bound, right? So when this happens, we say it's infinity, right? Now again, you can write down a precise definition for that. You can say for each, for any positive number you pick, you can find a number sufficiently close to pi over 2 on the left side of it that you make values of the function larger than that given positive number. If you can do that for arbitrary positive numbers, that means the limit goes to infinity. So you can state like the careful definition for this limit in terms of an if-then statement. But I don't think we need to do that. I think it's enough for us to look at the graph in here and try to understand it, right? I mean, people include this notation in pre-calculus sometimes, right? It's not a big deal. It's just a nice notation to express what's happening, right? How about this one? You guys can tell me. X goes to pi over 2 from the right. This one, right? What's this equal to? Negative infinity. So what do we say about the limit as x goes to pi over 2? The double-sided limit at what? We just write it does not exist, right? Because it's going to minus infinity on one side, it's going to infinity on the other. Okay? But the truth of the matter is the left and the right limits here also don't exist. And what you're like, what do you mean? I mean, they don't exist as real numbers, right? They're infinity or minus infinity. Those are not real numbers. This is a notation that expresses the function getting really large or really negative. Now, one more example here. I like this. This is the volcano function. I'll center it at 3. So what's the graph of this guy? If I write y equals f of x, what's it look like? Oh. I can get it more. This chalk is like bold compared to the other one, isn't it? It's way better. But I've only got this little nub of it left. So this looks like, I say it's a volcano, right? It looks something like this, right? So in this case, we can say that the limit as x goes to what? I said 3. X goes to 3 of 1 over x minus 3 squared is equal to infinity, right? In fact, the left and the right limits there both go to infinity, right? So as a point of terminology, what we're going to say is anytime you have a finite point, all right, and if the left or the right limits, or both, let's say it this way, if any of the right or left limits go to infinity or minus infinity, then we say that the function has a vertical asymptote at that point, right? If the limits at plus or minus infinity exist and are some number, then we say that the function has a horizontal asymptote at those points, all right? So now, what I'm telling you right now, it doesn't really have much to do with that tangent problem, right? But these are things that we're going to run into, and like one of our larger goals in here is describing graphs with limits, so it's just kind of part of the natural discussion. So I hope you don't mind me sort of rounding out our discussion of what limits mean here, all right? Now, at this point, I mean, there are other things that can happen. There's weirder stuff that can happen, right? Like, here's one. There are functions that look like this. Check this out. As you go to 0, from one side, it looks like that, all right? But from the other side, it looks like this. Oh, I shouldn't do that with that chalk. So like, I'm not quite doing it justice, but the graph of the function is just infinitely wiggly. Just wiggle, 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 like that on that side. If that sort of thing happens, the left limit, right, f of x goes to 0 as x goes to 0 from the left. So this is another notation I should mention. Like, we don't have to write limit. Another way is we can use arrows. F of x goes to 0 as x goes to 0 from the left is a notation we like to use sometimes. But on the other hand, the limit as x goes to 0 from the right of this one does not exist. And when this happens, we say it doesn't exist due to oscillation, all right? So that can happen. And there are all kinds of other weird ways functions' limits might fail to exist, but these are some common ones. All right, so in your homework, I have assigned you a like a proof of the of a function with the epsilon-delta definition. So I think it would be healthy for me to work an example that's exactly like your homework, so you can try to like mimic that for your solution if you want. So let's go through that here. So here's a sample proof for you. And the goal here is partly, ideally, this will help you understand the definition more. That may or may not happen for you, but anyway, here goes. So we wish to show the limit as x approaches, let's say, 6 of 2x plus 3 equals to 15. Directly from the definition, okay? All right, so when you're faced with a problem like this, like the first thing I usually do, or I encourage students to do when they're first learning, is to do some scratch work, like to try to decide, like, what am I trying to do? Like your goal here, so this is my f of x, right? And this here is the quote-unquote L in the definition, right? So what I want to make f of x minus L less than epsilon using that 0 is less than x minus 6 is less than delta. Sorry, this chalk is corrupting my handwriting. Oh, well. So what is, this is what? This is 2x plus 3 minus 15, right? How does that work out? That's 2x minus 12, right? We can factor a 2 out of that. That gives us what? Yeah, 2 times x minus 6, right? Now, we're allowed to make this less than delta, right? So this is less than 2 delta. And we want to make this less than epsilon, right? So if we set this equal to epsilon, it looks like we're in business. So so far, this is just the scratch work, all right? So if you didn't write any of this down, you could still get full credit for the homework problem, all right? But what you must write is what follows. So above is scratch work. Here's the proof. We begin by saying, let epsilon be greater than 0, right? Because the argument I'm making has to hold for arbitrary positive numbers. Then I choose delta equal to what? Well, this scratch work showed me I should make delta equal to what? Not 2, but can you guys tell me? So delta equals what? Epsilon what? Epsilon divided by 2, right? Solve for delta epsilon over 2. Delta is epsilon over 2. Now that is greater than 0, right? So that's good. We need that. Okay, so I made my choice, period. Now suppose x is a real number and 0 is less than the absolute value of x minus 6 is less than delta. All right? I usually write consider. So English majors would not like this at all. Like if you look at 50 of my epsilon delta proofs, you'll find that there's really only about maybe 2 or 3 literary styles. I use the same stupid verbiage every single time. It's not very colorful, but, you know. So what I'm saying is consider. And then we're going to look at the absolute value of 2x plus 3 minus 15, right? This is equal to 2x minus 12. Now this should be deja vu all over again. I'm just retracing my steps. And that, of course, is equal to 2 times the absolute value of x minus 6. And that is less than what? This is less than 2 delta, which is equal to what? That's equal to epsilon, because we made delta equal to epsilon over 2. We're almost done. We just need a concluding sentence. Therefore, the limit as x approaches 6 of 2x plus 3 equals to 15 by epsilon delta definition of limit. So I'll tell you right now, if I do put this on the test, it will be exactly this kind of problem. All right? In my notes, I also show you how to go through like epsilon delta proofs for like a quadratic and for some more exotic things. But like, as far as the test is concerned, we'll just focus on just this linear kind of problem. All right? So if you can learn this, or if you can memorize it, if it's, you know, I've taught Calculus 1 a bunch of times. There is a subset of students who just when you hit this material at this point in your existence, like it's just not going to stick. And that's okay. Like it's not the biggest deal in here. There are other things that are much more important. But I'm sharing it with you because, you know, it is how we actually understand the limit carefully. Anyway, so there's that. Any questions about this? So one of your homework problems is almost the same. It's just got like a different number, I think, for this and that, but it's otherwise pretty much the same problem. Okay, so with that said, I'm going to shift gears here and talk about limit laws, all right? So if we always had to calculate limits from the epsilon delta definition, like we would never get anything done, right? This is like very, very tedious, even for a linear function, right? And it gets much worse when you get more complicated functions. So it's important to learn the theory of limits so that we don't have to go through these kinds of arguments ultimately, all right? And so I'll just write them down for you here. Limit laws. So assuming the limit as x goes to a of f of x, and the limit, well, let me give it, well, fine, and the limit as x goes to a of g of x exists, number one, well, one thing I should mention, the limit as x goes to a of f of x plus g of x is equal to the limit as x goes to a of f of x plus the limit x, oh, that's cool. You can actually write on this thing. X goes to a of g of x. So the limit of the sum is the sum of the limits. So we can break up across addition. We can also pull constants out. So like the limit as x goes to a of c times f of x is equal to c times the limit as x goes to a of f of x. There's also a product rule for limits. The limit as x goes to a of f of x times g of x is equal to the limit as x goes to a of f of x times the limit as x goes to a of g of x. So the limit of the product is the product of the limits, provided they both exist. You probably won't be surprised by the next thing I write. We can also do division. The limit as x goes to a of f of x, but now there's a string attached. You'll have to tell me. What's the string that I must attach to this result? Like this is not without qualification. What's the fine print I need to add here? Anytime you got division, you got to watch out for what? Division by 0, right? So this is only true if the limit of g of x is what? The opposite of that, yes. Non-zero, right? So the limit of a quotient is the quotient of the limits provided that the denominator function has non-zero limit. What else can we say? Five. We can write some more elementary results, like the limit. What was it? I saw a look of. Is this my writing?
Oh, no.
I was trying to teach my daughter yesterday, and she's making fun of my handwriting. She's talking all kinds of smack about my spelling and stuff. You guys are a little bit older, though, more respectful. It's good. You said your math education? What age do you want to teach?
Probably
9th or 10th grade. Okay. Yeah, there seems to be a consensus that people either want to teach the little kids or like the high schoolers. But what's in between, nobody wants anything to do with. A bunch of punks. I actually kind of like that age. I don't know, like I think 7 to 10 is fun, but 8 to 12 maybe, I don't know. Anyway, so limit is x goes to a of x is what? Here's a proof. Let epsilon be greater than 0. Choose delta equal to epsilon. Note 0 less than epsilon value of x minus a less than delta equal to epsilon implies the limit as x goes to a of x is equal to a. There you go. That's the proof that this limit is equal to a. Because you can make values of x arbitrarily close to a as x approaches a. I mean, surely this is not true. It's very bad language, right? I mean, but anyway, there's the exciting proof of that. Now, the proof of these is more involved, all right? And hopefully, I'm going to show it to you today, but I'm not going to write it out. We're going to hopefully use the projector to look at those. So that's one of the reasons I write notes, is because sometimes there's a proof which I really want you to be able to see the details of, but I also don't want to waste an hour of your time writing it out on the board. So that's one of the functions my notes serves in this class, is just to give you a repository of how things are done. Time is limited in here, right? There's only so much I can write on a board and tell you. So the lectures in here are our summary of the notes. Notes are much more expansive. My notes are almost always written for like an honors student overall, like the totality of them. I don't expect you to understand. There's something like 4 or 5 pages in my notes that just have epsilon-delta proofs of particular functions. I don't expect you guys to learn all that in here. So you can kind of skip past it as you're reading the notes, all right? If you ever, like, in doubt as you're studying my notes in this class, if that part of the notes actually matters a lot to this class, I am not at all offended if you email me and say, I don't quite know what's going on here. Does this matter that much? I mean, you can send me that email. I will respond. And I probably won't be coy. I mean, I'm probably going to tell you yes or no, you know? So, all right, so anyway. What else do we know? You notice that once you know 5, if you know 5, you can combine it with 3, and what do you get? Like, what's the limit as x goes to a of x times x? Well, that's x squared, right? So that's x times x, isn't it? So by applying rule number 3, what do we get? We get the product of these two, which gives us what? But we usually write a squared. And you can keep doing this, right? Like if you can do it twice, you can do it 3 times, you can do it 4 times. It's fairly clear that generally you can write the limit as x goes to a of x to the n is equal to a to the n. So we're starting to see a pattern here, right? For formulas, if the formula makes sense at the limit point, what do? We do the thing I was taking great pains to say we don't do in the motivating talk, right? We actually put x equal to the limit point, right?
What is that 5 and x? Just by the number 7, x and what?
That was supposed to be an n, as in nanu nanu. It's a Mork and Mindy reference, which is really a reference to a forgotten time. Do you know about the Mork and Mindy? Mork and Mindy is a situational comedy from the late 1970s, I believe, maybe early 80s, starring Robin Williams, where he made it famous. He played a alien named Mork, and his Earth friend was Mindy. And his famous saying from the show was "nanu nanu." So, I also bring culture into this class, you know, like so. There you go. But yeah, I think I've been teaching for about a decade, and even at the start of my teaching, that reference was dated. So, and I've never really watched Mork and Mindy either. It used to be on like Nick at Night with my grandparents' house when I was little, and it just, you know, when you're little, aliens are like, what's an alien? You know, it's fascinating, right? Let's see here. What else? This one, if there's fine print here, if the limit as x goes to a of f of x is equal to, let's say, L sub f, and the limit as y goes to L sub f of g of y exists, then I regret I've worked myself into a corner, but I think I can write it. Here goes nothing. The limit as x goes to a of g of f of x is equal to the limit as y goes to L sub f of g of y. What this rule says is you can make a substitution in the limiting process. If you have a composite function, if you understand where the inside function's going to, if the outside function has a limit that you also understand, then you can just trade it for that limit. I have examples of this we'll look at, but those are the big ones. Actually, I think it would be healthy for me to show you an example of 8 that might, let me not leave this so mystical. All right, so let's see here. What do we already know? We know that the limit as, let's say, y goes to b of y squared is equal to what? I mean, I use the letter x and the limit point A, right? But that's just a notation, right? We could, if we change the letters to y and b, it's still true. The logic of the math doesn't change when the letters change. This is just equal to b squared, all right? So this is nothing more than number 6, changing the letters, right? So consider, if we have f of x equal to 2x plus 3, all right, squared, then we can look at this as, oh, I'm sorry. I don't mean to say f of x. I meant to say, excuse me, just a second here. I'll get it eventually, guys. F of x is 2x plus 3, right? F of x is 2x plus 3. So we just got done, I just erased the proof of it. We know that the limit as x goes to 6 of this is what? By the way, just, oh, the epsilon over 2. Well, yeah, but that was the mechanics of the proof. Totally agree with you. What's the limiting value equal to, though? The big L, I called it, in that the limiting value there was 15, right? And how is that? How did I get that anyway? All you do is plug 6 into here. Why you been talking about all this crazy epsilon-delta nonsense when all you got to do is just plug in the number, right? It's just to confuse the students, right? So that's 15. I am joking about confusing the students, to be clear. Sarcasm is sometimes lost. So 15. So I know that limit's 15, right? And if I was to look at the limit as x goes to 6, right, of 2x plus 3 squared, the limit composition rule says I could trade that for the limit as y goes to 15 of y squared. Here I'm saying y is equal to 2x plus 3, essentially. This is what rule number 8 says. If you understand how the function of the inside, if you understand the limit of the inside function of a composition, what it goes to, you can trade the limit for the given variable for a new substituted variable, where the new substituted variable limits in the natural way, because 2x plus 3 goes to 15 as x goes to 6. So I trade my limit for x for a limit for y, and this is nothing more than y squared under that substitution. And then what's this? This is, by this rule up here, with b equal to 15, it's just 15 squared, right? So the answer is 225, for what it's worth.
That was a problem in the test. Our answer would be 225.
Mm-hmm. Right. You're like, would you ask me to prove this using epsilon-delta definition? The answer is no, I'm not a monster. I already told you, only the linear case for the test, right? So, also, something else I should mention for the test that should make you feel a little bit less anxious. I will let you have a page of notes for the tests. You should be, as you're studying, collecting definitions that you want to know. And on this page of notes, I never put restrictions. Like, you can put whatever you want. Scripture verses, Elizabethan poetry, the words to this song the dwarves sing in The Hobbit. I don't care. Whatever you want. Or examples from this class. But it's up to you. Now that I personally benefited from classes I had as a physics major, which did this. Now, in the midst of battle, as I sat and looked at this impossible physics test, and I had my sheet of notes with size 6 font written in the smallest, size pen I could get, trying to squeeze every ounce of wisdom from the book into my page. I found that I never actually looked at the page, but the process of preparing that page prepared me for the test, in my experience. And so I'd like you to have the same freedom, and I'm telling you now so that you have a chance to make it a routine of your studying to try to build towards that. Anyway, let's see if we can. I want to show you the proofs of some of these things. Some of them are easy, and it wouldn't be insane to actually ask. Wouldn't be insane to ask you to prove. In fact, but that's another thing. Is if I want you to be responsible for the proof of a theorem on the test, I will probably tell you. Now, I do realize that gets to be a little bit silly because I'm also giving you a page of notes, so it's like you copy the proof down and then copy it down again, but what can I do? I guess I could be meaner and not give you a page of notes, but again, I had professors who did this for me. They said, you're responsible for the proof of such and so forth on the test. Now, admittedly, for some of those classes, I didn't have a page of notes, right? But it was useful for me. Now, all right, so let's see if I can get to where we need to go. Let's see if I can get this. Come on. That's not what I want. So many choices. I gotta mess with the zoom.
Got a little yellow line on it.
Oh no. That's different. Oh, that's weird.
It is weird. I'll have to tell you about it.
Huh. I wonder if my camera's near death. That would be sad. I've had this thing for like 5 years. That is very strange. Well, we'll see later in the video when I look back at it. But listen here, guys. So these are the course notes. This essentially is your textbook, right? And so we've skipped chapters 1 and 2. But I would like to point out to you some features of my notes. Like this is hyperlinked, right? So if you click on these, it'll take you to the part of the notes where it is. Like if I want to go look at set theory, there it is, right? I regret that because now I want to go back. Unfortunately, I don't know, maybe you guys can find a PDF reader which is better about going back and forward. This is my principal annoyance with Adobe is if I click on a link, then how do I get back to where I was? Do you guys know? Is there a simple way to do it? No? Okay. I mean, it's possible it's there. I just don't know about it. Now, and then limits, this chapter 3 is where we've been. All right, so here's what I was doing last time. Okay, so I started with that tangent problem, remember? And in the notes, which I've just posted, so you guys haven't clicked on them yet, right? But if you do, see, if you open it up electronically, see that right there? Clickety, clickety. And come on. Are you kidding me? To use Desmos, you need to update your browser. Oh, you. Well, that is aggravating. You guys will have an up-to-date browser. So when you click on that, it's going to work. So what that should take you to is a website, which actually allows you to move this point along the circle to different points and see how the line changes, all right? So hopefully next class,